Hello everybody, welcome to this doubt clearing session on our graph algorithms lectures. So today we will go through the doubts that have been expressed by the students and we will go lecture wise. So in the first lecture was introduction to graphs, and on that lecture we have several doubt clearing questions which we shall answer now. This is the first question. The first question was to elaborate more on hypergraphs. Just to explain to you, we had said that a graph consists of the following. The graph consists of nodes and edges. Typically, if there are four such nodes, then we had said that the edge could be an edge between any two nodes like this. But as you know, these edges are relationships, and these relationships, in the case of these edges between two nodes or connected between two nodes, is a binary relationship. However, as we have seen before, that relationships in general can be many, and therefore if a relationship has got more than one node or entity in the relationship, we get, instead of edges, we get what are known as hyper edges. Consider a relationship of a family, and let us say that these are persons in a family, and a relationship is a connection if they are part of the same family, which means it is the husband, the wife, the children, and suppose that this is the relationship. Then maybe x1, x2 and x3 are related because x1 is the husband, x2 is the wife, and x3 is the child. On the other hand, the wife x2 may be a child of two other people. Maybe that is x4 and x5. Whereas we may also have some x6 and x7 where x1 is the child of x6 and x7. So these are hyper edges. There may be multiple children, somebody may have 3 or 4 children, and so on and so forth. This is how hyper edges are created, and in general hyper edges can connect any subset of the nodes. So this is how we get hypergraphs or hyper edges in graphs. These have more complex applications. We are not concerned with those algorithms for hyper edges in this course. The second question was on layouts, and we had done this example on layouts, as you can see in this figure. These examples are about rectangles, and suppose that we want to represent the logical relationship between rectangles. So here are rectangles and we want to express logical relationships. So each rectangle is a node. Is a node in the graph. And how do we connect with edges? Suppose there are these 3 or 4 nodes, then we connect it with edges, and these edges are if they are adjacent. So adjacency marks the edges. That means if we say that the box B, node N1 and node N2 must be next to each other, that means in the physical layout they must be next to each other. Then we will connect it something like this, and in that case they will have to be placed in such a way that there is nobody in between these two nodes. So this is the logical relationship. The other question we may have is a physical relationship. So in the logical relationship, all we will have at a node is the dimension of the rectangle. Whereas in the physical relationship, we will also have the location information. That means we will have the center, not only the dimension, but the center coordinates. And once we have the center coordinates, we may have edges to demarcate something else. For example, in between these two rectangles, there may be a passage. Suppose this is a room. Between these two rectangles, there may be a passage, which means they are joined to each other, as we had mentioned in the original lecture. So the edges may be they have a joining, or they have a common boundary, and so on and so forth. This is how we represent layouts as graphs. We could do them as a logical layout, or we could do them as a physical layout. The next question is that if there is an edge, do we give 1 or 0 weight, or is it just a relationship? So in general, it is a relationship or a connection. The weight on the edges will come from the meaning of that relationship. For example, in this one, 2 down and 7 across are related. So node 2 and node 7 are related. This edge does not have any weight. It just expresses the constraint that the fourth element of 2 and the first element of 1 must be the same letter. So here is a constraint. On the other hand, if these were cities, this could have just been saying that there is a road. Or on the other hand, it could give a weight saying that this weight is 1 or 0. So the 1 or 0 can be a logical relationship of existence. 0 or 1 could be logical relationship of existence. It need not be a weight, or it could also be a weight. So sometimes when a 1 is there, means that there is a path, and if we want to find a path, we find the length of the path. On the other hand, the exact weight could be the exact length, the exact cost, and so on and so forth. The next question is about whether the adjacency is just a linked list. Then is it like this? Could it be this way or this way? Yes, it could be anything. However, its usage will depend on the algorithm. Now the algorithm may want to traverse all the linked edges from a particular node, and if it does not matter the order in which it is traversed, then you could do it this way. So it does not matter. It depends on the algorithm and the usage. The question is, could there be a graph with both directed and undirected edges? Yes. The example that you have given yourself is about voltage source and current source being directed edges and resistances being undirected edges is correct. In general, the edge could be having multiple relationships. So there could be multiple edge types in a single graph. In areas where you come to problems called semantic graphs, then you can express many types of relationships. One edge could be the distance edge, one edge could be the neighbor edge, the other edge could be some connection or constraint between two nodes. So every edge, so there can be multiple types of edges, as I have mentioned. In this question, in this slide, the question was if 5 and 7 is a constraint, which means 5, this is this node 5, and this is this node 7. The constraint is if they have a common letter at some point in time. Then you are asking whether 7 and 8 must have constraint. But 7 and 8 have no intersection. 7 is 7 across, 8 is 8 across, and they are not related to each other. On the other hand, 7 is 7 across and 5 is 5 down. So the second letter of 5 and the second letter of 7 must match. That is how this constraint has come. Next we said that should we connect the nodes using pointers as in a multidirectional linked list or store it in an array? There are many options. Now both arrays and linked lists can be used. Linked list can also be implemented by arrays or dynamic data structures. So the graph, when you do something like a sparse graph, where there are very few edges compared to the possibility of the number of edges, because there could be order n squared edges for n node graph, but sparse graph may have very few edges. In that case, typically a multidirectional linked list is used. We have not covered sparse graph algorithms, but there are some specialized sparse graph algorithms where these are used. Now we come to the second lecture on traversal of undirected graphs. Here you had mentioned that when we are enqueuing adjacent nodes, do we need to check whether it is already present? We are already checking here. If you notice that we are checking whether it is already present in the queue indirectly by the visited node. But if you want, you could also mark an array nqi, which whenever a node goes into the queue, you mark it as nq, and whenever it is taken out of the queue, you mark it and mark nq as 0, and whenever it enters the queue, you mark nq as 1, and all you need to do is you can check it in the queue. But in this algorithm, it is not necessary. The visited part takes care of it already. The next question was whether the cost should be initialized to infinity. As I had mentioned, there was a typo in the discussion there. The slides that were given to you have already been made this into infinity. So elaborate how this finds the shortest cost path in a weighted undirected graph. We had discussed a detailed algorithm of the shortest cost path in a weighted directed graph, and we have said that for an undirected graph, you mark both the edges this way. The undirected edges converted to two directed edges of the same weight, and the same algorithm which we did, which was the best first algorithm, will work. So we have done that in a best first search algorithm, which is also known as the Dijkstra's shortest path algorithm. And then we have done several other algorithms which take into account negative weights, negative cycles, and all that. Those were done in subsequent lectures 5 and 6, and I think you should have a look at those lectures and you will get the answer. The concept of timestamp, you have asked, why is the concept of timestamp required? In undirected graphs, timestamp is not so important because all we used it is to find the component number. And this component number, so for example, when you enter this node and you come out of this whole component, so you will see that the timestamp of entering this and coming out of this, there are two timestamps you can have, the entry timestamp and the exit timestamp. If for a node, the entry timestamp and the exit timestamp, for example, if you start with this component first and this component second, you will see that the entry timestamp of this node and the exit timestamp of this node will be earlier than the entry and exit timestamp of this node, which means that they are in different components. But there was an easier algorithm to find components, which we did here, so we purposely did not put the timestamps. But the timestamps of entry and exit were all put in a directed graph, and you must have seen those detailed algorithms. Now we come to the pathfinding algorithm. How many paths can be there in a dense graph? It is unclear how a path between any two nodes can be found by parent pointer links. You know, in a DFS, as soon as you go from one node to another in the DFS search, even though there is a graph here, if you go from this node to this node, you are marking a parent pointer like this. So as soon as you traverse nodes, you mark parent pointers. As soon as you traverse nodes, you mark a parent pointer. So as soon as you reach a particular node, and if it is a connected component, then traversing back through the parent pointers will give you the path back to a node. It need not give you the shortest path, but it will give you some path in a DFS. So that is how you go back through the tree edges, and along these tree edges are the parent pointers. So it marks the earliest parent, or one whose path from the start is not necessarily the shortest, but in the sorry, this is not correct. This is not correct. So this is the path according, or in BFS it is the shortest, but not in DFS. I'm sorry. Let me erase this a little. So in DFS it need not be the shortest, but in breadth first search it marks the earliest parent, as we have seen in the BFS algorithm. Therefore, for BFS it also gives you the shortest cost path. There may be many paths depending on the number of cycles. I had given it to you as an exercise to find out how many paths can be there from one node to another, and whether including cycles, excluding cycles, and so on and so forth. So this is a very interesting way to find out how many paths can be there. And I had left it as an exercise, and I will leave it as that. So the path finding using DFS, all we need to do is traverse back through the parent pointers. Once you have found the goal node, once the goal node is found, all you need to do is traverse back through the parent pointers. And do we have to traverse parent links every time for a different pair of nodes? Yes. It depends on how you have proceeded with the algorithm, because if you have an every pair of start and goal nodes, then it depends on how you have proceeded with the algorithm. So you would, and for DFS it will be different for different paths, and depending on how you have seen the order in which you have seen the children. Breadth first search. So we have seen breadth first search is an effective to find the shortest cost path. BFS can be modified to find shortest cost paths in weighted trees, and we have seen that. So I hope you understand the requirement for it now. Here in this algorithm, you said that link 4 to 8 is a back edge. Then the graph, if there is a back edge, does the graph have a cycle? Yes. A back edge comes when a node is, so a back edge, when does a back edge come? A back edge comes when you visit an already visited node. For example, in this case, we had visited this was marked visited, then 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 this was marked visited, and this became a back edge. Then this was marked visited, then this was marked visited, and again this part became a back edge. So there were two back edges, and as you can see, if a node is already visited and you come to it with a back edge in an undirected graph, then there is a cycle. Can DFS be done iteratively? If it is a single connected component, then DFS will cover all the nodes in the graph. But as we have seen, if there are multiple connected components, then it will cover only that connected component in one iteration, and then you have to go through multiple iterations. And this iterative DFS algorithm was shown in the connected components case, where we presented that algorithm here. Here, this was the DFS where we found one connected component, and here is the iteration where we For each node, if visited is 0, we increase the component number and recursively call it. So this is how we iterated. So that is what we had done in this iterative version. So this algorithm we have seen, and therefore we have seen this for component finding. How would you find the level or depth of a node in BFS? We had done this algorithm subsequently, and we have seen that every time whenever we mark a new node, and this is a new node, which means a node is not already visited. So what did we do? We removed a node from queue, marked it visited, and for all children of that node, we check first whether it is visited. If it is not visited, then we know we have come to it for the first time. In BFS, you can show that if you come to it for the first time, then you come to it with its shortest cost path. And that is where we increment the length by 1. And this length will give you the shortest cost path and the length of the path, and we can easily use this version of the algorithm. How do we get order V plus E in DFS and BFS? The question is, each edge is examined once in one direction and once in another direction. So in two directions, when you go from here to here and here to here. So now each edge is examined constant number of times, and each vertex is recursed once. So based on this, you have order E is because the constant number of times an edge is seen, and V because a constant number of times a vertex is seen. Similarly in BFS again, you put a node in a queue and you take the node out of the queue. You take the node out of the queue only once, and you may put a node in the queue only once, and every edge to that node checks it whether that node is already in the queue or not through the visited link. So that is how you get order V plus E. Now we come to the third lecture, which is the traversal of directed graphs. In directed graphs, you asked about this cross edge. So let me explain what this cross edge means. I had mistakenly mentioned about this. So the definition of cross edge is correct. The definition of cross edge, as we had said, was the entry and exit of a node V is both less than the entry and exit of a node U. Only then there is a cross edge. Let me show it by the example here. In this example, suppose we start from this node. Then we will do this node. We will enter this node. We will come to this node. We will enter this node. We will come to this node. We will enter this node. This is the back edge. We'll come back, and therefore the entry of this node is 1, the entry of this node is 2, the entry of this node is 3, the exit of this node is 4, the exit of this node is 5, the exit of this node is 6. Next, if you start from node, let us say you start from node A, then you do node A, the entry of this node is 7. Then from A you come to B, the entry of this node is 8. Then from B you come to this node and you back out of here. Then you come to this node, entry of this node is say 9. I'm doing in a different order that we had done in the class earlier, but it does not. Then this node, when you come back to this node, this is a back edge. This is a back edge because it has come to an already visited node. But then from here you will go to this node, And once you go back from this node, then this node is exiting from this node, and you will get its exit value to be 10 because you are exiting from here. Though before exiting from here, it will also check this edge. Now you notice that for this node, its entry and exit are less than the entry of and exit of this node. Therefore, this edge which we see here is a cross edge. Similarly, you will get this edge to be a cross edge. Similarly, you will get this edge to be a cross edge. So as we had said, the definition was correct. There was a little mistake in my expression of that sentence, and therefore this is how a cross edge is done, and this is how a cross edge is used. Now, I hope that clarifies the doubt regarding cross edges. We next come to topological ordering. So here is an example, and the question was, where is topological ordering used? As we had mentioned, this is about an evaluation of an expression. At this node, we are evaluating the expression a plus b. At this node, we are evaluating the expression a plus b, which is the outcome of this, into c. So at node A, we are evaluating this. At node B, we are evaluating this. At node C, we are evaluating A plus B plus E. And at node D, we are evaluating whatever we got in B and whatever we got in C. Now you notice that there is an ordering of this evaluation. This ordering of this evaluation, I can do A, I can do A, I can do B, I can do C and D, or I can do A, I can do C, I can do B and D, or I can do C, I can do A, B and D. But what I cannot do is I cannot do B, A, D, C. This is invalid. This cannot be done because its preconditions or precedences are not met. So a topological ordering maintains the precedence constraints, and finding a topological ordering is important to find out how to evaluate. Here is an example of topological ordering. Next, we said that DFS is called multiple times, and the choice of the node matters. For which, so is there any efficient way to find the coverage? No, there is not. Because if we, for example, here in this case, if we did D, then we would have got this. But if we started with A, we would have covered everybody else. But that does not matter, because for us, we will just do it iteratively with an outer loop and find out every node is visited or not, as we have seen. If we try to first find out which node passes through everybody else, then this pre-processing time itself will be order V plus E. Our algorithms are in any way ordered E plus V. It visits every node once and every edge at once. So why do we need to do any pre-processing? So it does not do that. It is not necessary. By an iterative outer loop, we can easily do the same thing. We come to the fourth lecture on minimum cost spanning tree of a graph. The question was that here is an algorithm which somebody has proposed. Initially go to any node, mark it visited, and then among the unvisited successors of that node that is connected through a minimum wedge, you go, there is no successors, then backtrack. So suppose there is a graph like this. So this is V1, this is V2, this is V3. So we would have, how would we have proceeded with the algorithm? We would have done V1 in by the algorithm proposed. From there we would have gone to V2, and from there we would have gone to V3 by this edge. But if we chose this edge, then this edge does not give me a minimum spanning tree, because this would give me a spanning tree covering these 3 nodes of cost 11. So we would rather have to choose this edge, which means that what we are doing is a slight modification of what you have said, is that we have these 2 sets. Instead of finding the shortest cost path from the last edge which is taken here, we find the shortest edge from all the vertices of this node into this node. That is how we get the minimum spanning tree. So the greedy algorithm is a slightly globalized greedy algorithm than just visiting the shortest edge from the last node which has been included. Some parts of Kruskal, how are cycles detected? I think there was the set union find algorithm which was discussed about how cycles are detected, and that set union find algorithm proceeded as by this. If find set u is not equal to find set v, and I think Dr. Hazra has given you a detailed exposition of that using the union find data structure. Here you said we had mentioned the condition as that while E is not empty or V, it should be while E is not empty and V, which you are right. This is what it is. So this is how the algorithm should. So this, while this is or V naught is equal to V, and so as long as E is not empty and V naught is equal to V, Vt is not equal to, so this is what the algorithm should be. Kruskal's algorithm, what does the find set operation mean if we don't use hashing? I think this has been discussed in details in the disjoint union find data structures lecture, and if you follow that you will get it. How does the complexity come like this? In Prim's algorithm, in Kruskal's algorithm, you need to sort all the edges. So if you sort all the edges, you get order E log V. And in Prim's algorithm, from one set to another, you need to find the minimum weight. So what we are doing is we are maintaining a min heap, and using that min heap data structure, we are, as soon as we draw one node from one set to another, we start including some edges. So we insert edges into the heap, and from the edges into the heap, which means all the edges which are from this side to this side, and as soon as you include one edge, some more new edges come in, and as soon as you choose one edge is deleted. So you have got a delete or a delete min from that, and based on this you use, so every edge is put at most once, therefore you get order E log V. But you know, there are Fibonacci heaps which you can use, and using Fibonacci heaps you can do a much better algorithm, but that is out of scope of our lecture. The other thing we said is, before we move to the greedy algorithm, there was the recursive algorithm, and you wanted to know what is this value. What does this algorithm do? Let us see. What this algorithm does was, it had 2 sets, G1 and G2, and the edges chosen in G1 was T. The edges chosen in G1, which was the spanning tree of the nodes of this, is T. Now from here, suppose there are 2 edges, then the algorithm recurs in 2 directions, one to choose this edge and one to choose this edge, and in each case we made one G1A and G2A, and we made TA. TA was made by adding this edge in this part and this edge in this part. So at any point in time, G1 contains all the edges chosen in the spanning tree. Therefore, when G2 is null, you return the spanning tree of that branch. And therefore, whatever is returned back from this side is returned back by that mechanism. So the tree that is obtained out of the recursion of this side is done that way. Let us see here. In this case, we start with node E and we have got 3 edges. So we will recurse in 3 directions. In one, we will choose this edge, which means this will become G1A and this will become this. So now, as in G2, we have already sent this edge, and after the recursion, all the minimum spanning tree that is chosen out of the recursion coming of this plus this edge which has been sent here, because we are sending that edge TA back here, will come back as T dashed. Similarly, if we chose this edge, that means here, then this would become G1A and this plus this would become G2A and whatever comes back. Similarly, if we had chosen this edge, then this would become G1A and this would become G2A. And each of these 3 would return some T dashed. So T dashed would come from one of them, T dashed would come from the second edge, and T dashed would come from the third edge. And this would go, the recursion would go in these 3 directions. And of them, each would come back with a cost. We would add the edge cost. That means in one case we'll add 11, in another case we'll add 3, the third case we'll add 4. And whichever of them is the minimum, that T dashed is chosen and as T min. So that is how we get back the answer to the recursion. But as we have seen in the greedy algorithm, the final greedy reduction says that you can choose exactly one of them and recurse, and you don't need to go back to all the 3 in the final algorithm. We come to lecture 5, which is on shortest paths in graphs. And in this algorithm, K is not in the queue. How do we check? Very simple. We could check with visited, but if you want to have a separate algorithm, you don't need an order n, because if the n nodes are known to you, all you need to do is mark an array in queue, which is marked as 0 if it is not in the queue and marked as 1 if it is in the queue. So a simple check on that in queue array is sufficient to give you an order 1 time check whether it is in the queue or not. The second is, why will the algorithm not work for directed acyclic graphs? In a directed acyclic graph, in a directed cyclic graph, which we have, coming back to a node does not necessarily mean that there is a cycle. For example, as we had seen, that if you are going to a node, say you mark this as visited, then you come here, mark this as visited, and then from here you backtrack here, you come here, whereas this edge is a back edge. On the other hand, when you come back here and come back to this one and come back to this one again, then this path is, you are coming back to an already visited node, and therefore it is not necessarily a cycle. As we have seen, a cycle can be formed by a back edge, in a DFS, but there could be other places where you come back to an already visited node through a cross edge, and that need not always be a cycle. You could also come back to an already visited node by a forward edge. So in DFS, you really can come to a node with a much larger cost, and because of that you need to backtrack. I had given that as an exercise. So This algorithm, if you look at several algorithms for this node, you will see that you will need to backtrack if you use DFS. On the other hand, if you use BFS, you need not backtrack. Then we come to this all pair shortest paths in the graph. Unfortunately, no queries have been asked in this. Please go through the lectures. If you have any further queries, let us know, and then we will try to clarify those queries.